We're going to talk about today a fundamental principle in calculus, which is limits, which is really helps us understand integrals and derivatives kind of in the next couple sections. So what we want to do is we are looking at a function as it approaches a right here. And you can see that a is really our x value. And pretty much what we're trying to figure out is what that y value is going to be as it approaches the number. So visually, what we're looking at is we're looking at as our x values of our graph approach that number, what happens to the y values. So as this x value gets closer to here, the a, what is that y value going to be? And you can see we can look at it from this side and this side of the graph. So as the x values get closer and closer to that value, you'll see that the y values also kind of diverge to that same point. So they kind of close in on it. So what we're looking at right here is we're saying as x approaches a in the function, what will its value be? And in this case, the f of x value, your y value, is approaching the value of L. Let's look at example 1, something a little bit more concrete. And we're going to look at it not only visually this time, but we're also going to look at it through its table. So what we're going to do is take a look at the function 3x minus 2, and we're going to look at the limit as x approaches 2. So this is clearly a linear line. So if we say f of x equals 3x minus 2, this is a linear line graphed to the side. And we can see when x is 2, we can clearly see what that value is. But what we want to do is we want to look at what is happening on both sides of the equation. So from the right side, you can see it's closing in on this point as it goes from infinity to 2. It's closing in here. But as it's coming from negative infinity to 2, it's closing in on that same point. Now, it won't always be closing in. Sometimes it might be open, but in this case, it's very clear. It's coming in to one specific point. We can kind of look at a t-chart and see what happens as we get closer to 2. So if we take 1.9 and plug it in, we're going to get 3.7. If we put in 1.99 into the equation, we're going to get 3.97, and so on. And then this one will be 3.997. We skip this one real quick. Now, if I come from infinity to 2, and I plug in 2.001, we're going to get 4.003. And then we're going to get 4.03, and then 4.3. So you can kind of see how these numbers are going away while this one diverges, or as I'm approaching from this side, it's closing in on the number, which will be 4. Now in this case, if I actually plug it in, 3 times 2 minus 2, that does give us 4, which is what the limit does approach to. Now the second example is a little bit different. You'll be able to see why plugging it in doesn't always get you to where that limit is going to be. So let's ignore the graph on the side for a second, and let's just plug in 3 into our function, which is x squared minus 9 over x minus 3. So if I plug in 3, we're going to get 3 squared minus 9 over 3 minus 3. And this gives us 9 over 9 over 3 minus 3, which is 0 over 0. Now, obviously, that doesn't work. That doesn't give us a value. This is called an indeterminate form. And so if we try to plug it in with the original, we know it doesn't exist. Sorry, intermittent form. So it doesn't work, right, when we plug it in. So if we look at this, though, this is something that we have seen way back in semester 1, where we can take this form and I can factor the numerator, and what we end up getting is just x plus 3. And with this, we know that it is all real numbers for the domain, except for when x equals 3. And that's because of the denominator, x cannot equal 3. Now, if you recall, this made a hole in the graph, which we see right there. So, same sort of idea and principle. I'm going to graph this, right? Y-intercept is 3, slope is 1. And as I'm approaching 3 from this side, and then approaching 3 on this side, I want to look at what's happening. And even though the value doesn't exist at 3, it is still a limit. And I can plug that in. So I can take the 3 and plug it in. So 3 plus 3, that limit is going to be at 6. At this hole in the graph, or this popped point, which is 3, 6. So what we say is the limit of f of x as x approaches 3 will equal 6. I'm going to come back to number 3 till right after our theorem in a couple minutes. We can also look at the limit of a graph from different sides. So we can approach it from the right-hand limit, or we can approach it from a left-hand limit. Now, if it's a right-hand limit, it will have a plus sign on it. And what that means is that you're coming from the right side. So you're going infinity, positive infinity to negative, or towards the point. So you're going right to left. Whereas with a left-hand limit, it'll be denoted as with a negative sign in that upper corner. And you're going to be going left to right, approaching that point and seeing what's happening. So if we kind of look at it this way, usually this happens with disjointed graphs. Sometimes it'll be the same, but usually it's going to be disjointed. And you can see if I approach this function from the right side, I'm coming in this way. So the graph starts over here. So I'm following this graph along this way. And I see as it approaches the number, that y value is at a different height than if I were to come down here and approach it from the left. If I approach it from the left, it only has a height, or a y value, of L2. Again, when I come in from the right, it has a different y value, which is L1. Now, that's kind of important to understand, because the first two examples that we saw, when we came in from the left and the right side, they kind of closed in on exactly the same y height. But again, as I just mentioned, that's not always the case. And this comes to our theorem right here, theorem A. It says if f is defined throughout an open interval containing a, except possibly at a itself, then the limit a equals L if and only if, when you approach that limit from the right side, and then from the right side, then from the left side, they give you the exact same value. If I approach it from the left side and then the right side, and they give you different values, then a limit does not exist at that point. So let's go back to this interval. So I'm looking at 0, right? So that's right here. And if I follow the graph this way, it's diverging positive infinity. Okay, it's not hitting a point. Where I'm diverging this way on the left side, it's not closing in on a single point. So it's not going to exist. Let's look at example number 4 real quick. The function is the absolute value of x over x. And I want to look at it from the right-hand side of 0 and also the left-hand side of 0 and then see if that limit exists. So if I plug in 0, 0 over 0 does not exist. If I plug in 1, 1 over 1 is 1. If I do 2, 2 over 2 is still 1. If I plug in negative 1, that's absolute value over negative 1, so it's negative 1. And again, I'm going to get negative 1. So what happens is I have this graph, and at 0 it doesn't exist, but at 1, 1 it does. At 2, 1 it does, and it's an open circle, horizontal line this way. Okay, so when the positive numbers are this way, and then at negative 1, 1, negative 2, negative 1, when I plug in negative numbers, it gives me a horizontal line going this way. All right, so looking at this first one, coming from the positive side, if I'm at the graph approaching this way, diverging to 0, the point at 0 has a value of 1. So as I approach from the right to 0, that's why I'm finding the limit at the right-hand side is 0, the y value is 1. So that height is 1. Now, compare that to this one, the middle one, where I'm coming from the left-hand side of the graph. As I approach 0, what is the height of this? Well, the height now is only at negative 1 because it's coming from the left. It's following those negative numbers. Now, again, because I'm diverging on the left side to this number and the right side to a different number, they're clearly not the same. That means it does not exist. The limit does not exist because they don't match up. All right, last example. This is a piecewise function. So we have 2 minus x if x is less than 1. And then we have x squared minus 1 if x is greater than 1. So what I did is I graphed this right away. The red line shows me intercept of 2, slope of negative 1. But because it's less than 1, I have to cut it off right here, right? It only shows on the left-hand side. And then the blue is a parabola, shifted down 1. And again, I'm only on the right side of 1. So what's solid over here is the actual graph, and the dashed actually doesn't exist. So approaching from the right-hand side of the graph, so coming this way from the graph, when I get to 1, which is right here, that y value, or that height, is only 0. But when I come from the left-hand side of the limit and I close in on it, you'll notice that the height is different. The height is at 1 for that red linear graph. Again, because these are different, the limit does not exist.